Log on, tune in, find out. Another good idea from Cambridge.
Yes, it's a pleasure to have Hadi Godazgar all the way from over there to talk to us about, I'm looking at the title, M-theory dualities and generalised geometry.
I'd first of all like to thank the chair for asking me to talk about work that he obviously thinks is interesting. This work is done with these people and it's based on these three papers. So it's with Malcolm Perry, David Berman, who were on all these papers, Hadi Godazgar, who's on the second paper, and Pete West on the third paper. And I guess the real motivation for this, this is an outline of the talk, so I'll give the motivation, review some previous work, then I'll explain how nonlinear realization can be used to get generalized metrics, which are then used to write the 11-dimensional supergravity in a duality invariant way, and then I'll talk about the specific case of SL5 where we construct the diffeomorphisms in the generalized geometry and arrive at the section condition for that particular case. And then I'll make some final remarks. So the real motivation for this work is something that Bernard Julia found in 1981, which is that when 11-dimensional supergravity is reduced on a torus, one finds that the scalars live on these cosets. So this is the dimension of the torus, and these are the coset spaces. So this led to some conjectures that these dualities groups, which is the numerator on in these coset spaces, are symmetries of the full theory. There's in particular work by DeWitt and Nicolai, who showed that 11-dimensional supergravity could be written in a manifestly locally SU8 invariant way, covariant way, and later work by Nicolai for the SO16 local group. And so this is the motivation for this. And it's somewhat different from string theory, where as you go down the group is with ODD, because there's only the string windings which contribute, but here we have various branes that contribute when you reduce. So, given that I'm only allowed to talk for 45 minutes, I wanted to retaliate by not talking about the Berman-Perry work, but it's somewhat essential, so I will review it. Slightly quickly. So this is actually based on an earlier work by Duff and Liu, where they take the membrane action and they consider various rewritings of the membrane action. And so there's, I won't go through this algebra, but there's one way of writing it is to treat the coordinates as Lagrange multipliers for the action, and a second way is to treat winding modes as Lagrange multipliers. And then the equations of motion and Bianchi identities of these two actions are related by an object called the generalized metric. And so this generalized metric has also been considered by Chris Hull, particularly on his work on M-theory and generalized geometry. And there's also related work by Pacheco and Waldron, who in particular look at the case of the E7 group. And so this generalized metric can be seen as the the M-theory version of the ODD generalized metric that was talked about in the last talk. And it's completely analogous to double geometry, except that here the tangent spaces are extended by one forms as it is there, so these sort of correspond to windings of strings. But the tangent space is extended by a space of two forms. And the generalized metric will be thought of acting on these coordinates. So the Lagrangian of the M2 Reingold volume theory can be written in terms of this generalized metric. One can see that changing the coordinates, so doing coordinate transformation, has the effect of conjugating M. And so this is sort of what we mean by duality. Now, the idea in this paper of Berman Perry was to look at the d equals 4 example. So let me make a distinction between the number of dimensions of space that we had before in the work of Bernard Julia and this one. So in that case, in the previous case, one has 11d sugra, and this is compactified on Td to give a t-dimensional theory. And the scalars, when the reduction takes place, the scalars live in the coset space. However, the approach that's taken here is that you look at this bit, except that no killing vectors are assumed, so that the fields can depend on the coordinates along these directions, and then the action in this part of the space is then written using the generalized metric. So the fields have legs on this part of the space, but they depend on the coordinates in this space. And that is essentially what I've said here. So for the d equals 4 example, so in the work of Julia, that would be T4, which is the SL5, except it's and the 7-dimensional piece we sort of ignore. So what they do is they consider a canonical formulation because they want to ignore time. So they don't want the duality to act along the time directions because that complexifies the transformations. And so that's but they want dynamics in this, so the time has to be included, but not in the bit where we're describing it with the generalized metric. So that's the reason for the canonical formulation. And so we have the 4 ordinary coordinates plus the time that's sort of separate, and the windings of the M2, of which there are 6. And so this generalized metric is a 10 by 10 matrix. So, so in the canonical formulation, there's a kinetic term and a potential term, and both of these can be written in terms of the generalized metric. So, for example, the potential term is just r minus f squared, where this g is the is a Euclidean metric on the 4-dimensional bit, and the potential can be written in terms of these m's. So assuming that these fields are independent of the y coordinates, they rederive this potential. And as I said before, the kinetic terms can also be written in terms of this generalized metric. So this is analogous to the work of Hull, Zweibach, and Holm double field theory, where they also write the action in terms of this the generalized metric of ODD.
Can you write down the constraint in terms of this SL5 covariant metric?
Yeah, so that'll be at the end of the talk. That's the last section. So then, when I came into this, Dave and Malcolm were trying to extend this to go to high dimensions, higher than 4. So to do this for d equals 5 and 6, where the SO5 duality group in E6 duality group becomes relevant. And the problem that one faces is that as soon as you go higher than 4 dimensions, you've got to include the M5 brane. And the same argument that we used for the membrane to arrive at the generalized metric becomes technically unwieldy because of the nonlinear terms. So the same approach can't be used, at least we couldn't. So we have to come up with some other prescription for doing this, and nonlinear realization provides that prescription for finding the generalized metric. So the way that this was initially done was you've got to find the dimension on which this generalized metric acts on. And the way to do this is to count the number of winding modes. So for example, in 5 dimensions, there are the ordinary coordinates. There are 5 of those in 5 dimensions. There are the windings of the M2 brane, just like in the 4-dimensional case. So there are 10 of those in 5 dimensions. And now we have the windings of the M5 brane. It's an extra coordinate which in 5 dimensions can be dualized just to a scalar. So the number of dimensions on which the generalized metric acts is now 16-dimensional. This can be interpreted as the spinor representation of SO5. So let me briefly review nonlinear realization. So I guess this goes a long way back to what some would call, I guess, real physics in pion physics. And what was realized by these people was that the equations of motion of the pion physics can be written as a nonlinear realization of the chiral symmetry group. And one can think of the pion field as a Goldstone boson of chiral symmetry breaking, and this chiral invariance. So the chiral invariance is spontaneously broken and it's maintained by a connection that's nonlinear in the pion field. And this sounds a lot like gravity, where there's a connection which maintains the covariance via a term that's nonlinear in the metric. And in fact, it wasn't long before someone did this for gravity. And so Borisov and Ogilvy in particular showed that the gravity can be formulated also as a nonlinear realization. There's related work before that by Salam and Drafty and other people. And there are also nonlinear realizations in...
Can you explain what you mean by formulated? I mean, are there equations?
So they, in the case of Borisov Ogilvy, so they find the connection for the ordinary affine connection by essentially doing from the Moria-Cartan form of a group element, and then they say that So they have to use this Ogilvy theorem, which says that diffeomorphisms are conformal symmetry plus GL4 essentially. And then because they realize these two separate things, then they have the diffeomorphisms. And then essentially the method they use to get the action is one that we'll use. They said that, well, we want a diffeomorphism invariant action, and the building blocks that we have are the things that come from the nonlinear realization, and then they write the action up. I'll give the example for SL5, and it's very similar to theirs, except we haven't understood the connection for our case. So the nonlinear realization of a Coset space can be built from what's called the motion group element, GL times GE. So GL is built from a representation of the numerator group, and GE is a group element. It's in G. And so ignoring this piece, the translation generator. So this is effectively has the translation, it describes the translation generator. Ignoring this bit essentially describes signal model type thing. And so because there is a coset, the dynamics is invariant, and the left multiplication by the motion group and right multiplications by the denominator group, which will always take to be the maximally compact set. So this is obviously rigid, and this is local. So then we take the Moria-Cartan form of the group element G, and this splits into two parts. So the first part transforms covariantly under the local Hay transformations, whereas this bit transforms inhomogeneously. So that this piece is sort of related to the connection, and this to the field line. I make that statement a bit more precise here. The GL is a representation group element, so conjugating it by GE means that it still has to be generated by what are basically the translation generators. And so it can be written like this, where this object transforms under rigid transformations in its lower index and local transformations on its upper index, which is what smells like a field line. So then we interpret it as a generalized field line, and the generalized metric is just given by contracting the tangent space indices in the obvious way. So that this object is now invariant under local transformations, but it's got two indices that transform into the rigid transformations. So to construct the dynamics, we said want two derivatives only, and so up to integration by parts. There's 5 different terms that we can write down, and we want to calculate. So the name of the game is to try and fix these using either diffeomorphism or gauge invariance. And what we'll find is that imposing either one will automatically lead to the other. So in the case of Borisov-Ogilvy, they didn't need to do that because they essentially had the diffeomorphism from the realization of the conformal group on top of the affine group. We don't have the analog of that conformal group, so we have to impose at least one of them by hand, either ordinary diffeomorphisms or gauge invariance. So let me explicitly do this for the SL5 duality group. So the generators of SL5, the algebra of SL5 is basically this, where these M's generate SL5. So I'm sorry, I use M for generalized metric and here for generators. In this slide, M are the generators of SL5, and I'll let you know when they're the generalized metric later on. And we have these P's, which essentially generates representation of SL5. And in this case, they're the 10-dimensional representation. And so we have this. So this coefficient is fixed by requiring the Jacobi identity is satisfied, and this is fixed by the fact that Mij is traceless. Now, we're doing this in 4 dimensions, so we want to give a description of the fields in 4 dimensions. To do this, we decompose these generators into GL4 representations, so the Mij decompose like this, and the P's like this. So these are the translation generators for coordinates, and these are essentially the translation generators of the windings.
Sorry, before you go into about this, strictly those would be some weighted things, right? They would have the wrong determinant factor.
Yes, I will refer. So now let's build the nonlinear realization. We have everything we need. We have the group generators and the translation generators. So GL is this, and GE is this. So we've gauged away. We've used the local H symmetry to gauge away one of the generators. This one. And already by writing GL and GE, we've introduced sort of a set of coordinates and a set of fields. Then, as I said before, to find the generalized field line, we need to calculate this object, the Fourier-Cartan form of GL conjugated by GE, and then the generalized metric is found by contracting the tangent indices on the generalized metric, and we find that it's the same as the one that was found in Berman-Perry, except up to a conformal factor. And I'll discuss this conformal factor later on as well. And so this generalized metric can then be used to write down the action that was previously written down. So then in this paper, we go on to look at the d equals 5, d equals 6, and d equals 7 case. And what we do is so in the example I showed, we do the nonlinear realization for SL5. And in fact, one can do this for all of the others, except that the conformal factor one gets in that case makes the generalized metric have determinant 1. And so then a lot of these terms, so for example, this is essentially a derivative of the determinant. So this is 0. So then we can't use the generalized metric. Now what one can do is either do an arbitrary rescaling by det of G to then be able to have terms like this. Or what one can do is to assume that these duality groups are subgroups of some higher dimensional, some higher sort of larger group. which we take to be E11, and then in that case the conformal factor is fixed for you. And I'll say what the particular advantages of E11 are. So let me first go through each example. So in D equals 5, which is relevant for the SO5 duality group, as I said before, the generalized metric acts on the spinor representation, and we'd actually found this generalized metric a few months before using representation theory arguments, which is a lot more painful way of doing it, and I don't think we could have used that for all of the others. In D equals 6, the generalized metric acts on the 27, and this is the first case where the 6 form, in 11 dimensions, is dual to the 3 form appears. And of course, in D equals 6, it's got a vanishing field strength. And if we calculate so in each case, then we write down the dynamics in terms of this generalized metric and recover R minus F squared and R minus F squared here as well. So this is undynamical yet in D equals 6. In D equals 7, the generalized metric is 56 by 56 dimensional, and the dynamics of the 6th form appears in this example. So this is the action the one finds, the Lagrangian the one finds, assuming that the fields are independent of all the generalized coordinates. So we take the expression in terms of the m's and impose diffeomorphism invariance and outpop these two. Or we could impose gauge invariance and recover dr and all the other diffeomorphism invariant terms. And what's sort of remarkable is that the generalized metric is, in this example, sextic in the free-form field, and yet the expression that one finds at the end is simple. So now let me, so this was all done by taking these duality groups as being subgroups of E11 or subalgebras of E11. And let me point out the advantages of this approach. So first of all, there's no need to do some conformal rescaling. In fact, the conformal scaling that one gets from E11 is exactly the right one to even get this root G. So in all the other cases, one would have to then rescale the final answer by some determinant of G. Now, I think for me what's more important advantage of this E11 approach is that once one picks a particular representation of E11, and one may argue there's no reason to pick that particular representation, but once one does that, the dimension of all the generalized geometry in each case is given automatically. So if we wanted to do the nonlinear realization for each group, we'd have to count the number of windings. And I think this approach means that as we go on to D equals 8, for example, E11 will give a prediction of what sort of branes are in the theory that are whose windings are contributing to the dimension of the generalized geometry. But so this is all nice, but there are questions that remain. So we write these actions, but and then we show that when we take the fields to only depend on the x coordinates, we get the ordinary supergravity action. but we don't show any sort of diffeomorphism, any sort of generalized diffeomorphism in these actions. And even assuming that these depend only on ordinary coordinates is somewhat arbitrary. We don't have a reason for doing this. And in particular, it's not duality invariant. And the answer to both these questions is actually in constructing the generalized geometry, which I'll talk about next. So we've only done this for the particular case of the SL5 duality group. So the details of these formulae aren't important, but we write down the Lie derivatives in this generalized space. So these two indices run from 1 to 5. So XAB is some vector field for the case A equals I and B equals 5, and it's the Joule of some 2 form for A equals I, B equals J. So this is a vector field in the antisymmetric representation, and this is a vector field in the fundamental representation. And writing these in components, so without the indices running from 1 to 5, just substituting these in components. These are, in fact, the generalized Lie derivatives in Galtieri's thesis, where he extends the tangent space by 2 forms, which is a generalization of what Hitchin had done, where he extended the tangent space by 1 form. So in components, these are no different to those, except what we've done is wrote them in this sort of SL5 covariant way, which makes the clearly makes the SL5 more explicit. And we also define this generalized Lie derivative, which is found by taking the generalized Lie derivative of y along x minus generalized Lie derivative of x along y. And in components, this is just the Courant bracket. And in fact, dimensional reduction of this, if one dimensionally reduces along one direction, one gets the C bracket in ODD. Dimensional reduction, if one dimension reduces, this gives the generalized Lie derivative, or the Dorfman derivative in ODD, which is found by Grana, Minasian, and Petrini and Van Waldron. And this actually corresponds to, in the ODD, this corresponds to an ODD spinorial Lie derivative that's given in the paper by Quambra, Strickland, Constable, and Waldron. So under dimensional reductions, these are all related to the ODD generalized geometry objects. But now what one can do is to check if this geometry makes sense. One check is whether the algebra of this generalized diffeomorphisms closes, so that one just finds the generalized Lie bracket. And in fact, this only makes sense if this is satisfied on all the fields. So we interpret this as the section condition for this SL5 generalized geometry. And again, under dimensional reduction, this just reduces to the ODD section condition. And so the whole geometry only makes sense up to the section condition. So it only makes sense if one has a solution of this. And another example of this is that the Jacobi identity of this bracket is only satisfied up to the section condition. One can check that the non-vanishing of the Jacobiator is actually an exact gauge transformation on C. So that's physically, it's just a gauge transformation. Oh, and let me say that the actions we write down are actually invariant under these generalized diffeomorphisms. Which, it's a nice check that they make sense. So the choice we made before in deriving the supergravity actions from the duality invariant descriptions is a solution of the section condition, and one may ponder what other solutions correspond to. So there are other solutions of that section condition, and these may be involved. These may be related to non-geometries. Also, there's something evidently quantum mechanical about the section condition. So in ODD, the section condition corresponds to level matching in string theory. And so there's still the open question of if and whether the section condition in this case has any meaning in M theory. So let me summarize the talk. So generalized geometry gives a unified description of the free form and the sixth form and gravity all on an equal footing, and it leads to a duality invariant description of 11-dimensional supergravity. In particular, I've shown the nonlinear realization gives a prescription for finding the generalized metric, which is then used to construct this duality invariant dynamics. And this is an important point, that the generalized geometry only makes sense up to this section condition. So it's defined up to a solution of the section condition. And so for future work, we stopped at E equals 7. There's a question of E8, where we think that the dual graviton will come into the game. That's yet to be done. In the action that I wrote down in 7D, we got this, but of course, because we're in D equals 7, we don't know that these are dual to each other in 11 dimensions. So we need to understand how to get the duality relations between the potential forms. And there's some ideas on how to do that. Adding fermions, so the last talk was on extending ODD to the case where you have the fermions. That's yet to be done in this case. And we've written the actions, but there aren't geometric sort of underlying reasons for why these actions are there. So in gravity, you know that the action is a Ricci scalar. The interpretation of this is less clear here, although there's been some work by Quambra, Strickland, Constable, and Waldron along these lines. And stop there.
Could you explain a little bit more? You started with nonlinear realizations where you have G and H, but I think implicitly you have at least 2 Gs and 2 H. For instance, you have E11, the E11 plus the fundamental representation, and the maximal compact group, whatever that is. So, for instance, if you take ordinary fields on space-time, you have Poincaré divided by Lorentz of shape.
Yeah.
And that makes you space-time as a viscous space. And then the fields, because you not only look at scalars, a representation of the Lorentz subgroup. So, but here, the scalar fields, for instance, are cosets of E11 or subgroups of E11. So you have 2 cosets to do.
Well, the fields also here are in so GE is in G. So the fields are in the, what would be in your example, the analog, the Lorentz group. So GE is in our case in E11, not E11 semi-direct, the fundamental reps. Is that what your question was?
So, yeah, I mean, I'm questioning what is the big coset space you are talking about?
The coset space we're talking about would be Poincaré over the Lorentz space.
And taking values in what representation?
In the first, so in each example, there are different representations. In the case of E11, it would be the first fundamental representation. So maybe I'm misunderstanding.
The dimensions were given by the fundamental representation, but the fields are more like the adjunct of E11.
Yeah, the fields are in the adjunct.
Actually, coset of E11. E11 divided by.
Yeah.
So I don't exactly know what is being.
Can I add? Because I think one of the sources of confusion is, in any concrete calculation that's been done, E11 has been truncated to a subgroup. And there, when we have the subgroups, we know what we're cosetting by. You wrote down the cosets. So,
Yes,
so all that's talking about in terms of the representations is because it's how those subgroups are embedded in the E11 algebra, gives you some additional information. And that's all. So we didn't need to know anything about E11 over the real coset of E11 over something. We didn't need to know. It was just literally from how you truncate E11 into some representations.
That's fine. Then I want to understand how we put the translations on top of that. The coordinates, generalized coordinates.
The coordinates only come in via this GL.
L1.
So again, in the case of E11, the representation, just like the E11 itself, can be truncated to the subalgebras that are described by these. In the same way, the first fundamental representation is truncated. And so, for example, if one considers the truncation to d equals 4, where you have the SL5, one finds that the generators of the first fundamental representation of E11 under this truncation then give generators that essentially generate the 10-dimensional representation of SL5.
But just to be concrete on one example, take SL5.
Yeah.
So your space-time, general space-time will be homogeneous SL5 divided by SL5.
SL5.
No, SL5.
No, it's the local is the local group is SL5.
I mean, yeah, but then what's the dimension of the coordinates? Then you have many more coordinates.
So the coset for 5 dimensions, right, is SL5 over SO5.
SL5.
Yeah, but if you don't look at the system representation.
Right, and then so your question is, how do you know what the coordinates are?
That's right.
So you've got the SL5 is in the 10, and so you basically form a module of what the 10 acts on. And so we have them written down over there, effectively, where you've got those XABs. Those are in the 10 of SL5 and are acted on by SL5. So those, if you like, would form a representation, level 1 or whatever the term is. It will be acted on the adjoint of SL5, and so they will form a set of coordinates that you then translate. Those are the things which you then project. Is that okay?
That's right.
Okay.
I have a
Cool.
question. It's just to do with the meaning of the indices on the various coordinates. Because what it kind of looks like is that there's take the xi and the y's that you've got, on the one you've got up there.
Yeah.
So I mean, it looks like this, and that's some 4 plus 6 with 10-dimensional, or we 5 plus it's 11 or 7, whatever. But it looks like you've got some space where the structure group is not the, it's some kind of reduced orthogonal group.
So
10-dimensional space, and you have O4, and everything is broken with respect to that.
so
So that's, I guess, the question. But I mean, in general, you write down a coordinate. Coordinates aren't vectors, are they? So I mean, on the other, what we seem to have is a coordinate with two, that's in some sense an antisymmetric tensor. But how does that make sense? Because even the one with a single index can't be viewed as a vector.
well, I guess.
So, I mean, to be a coordinate. So I'm a little bit confused as to what the indices mean, because if you're in flat space, you just write x mu and transform Lorentz transformation, it's simple. But if I'm in some kind of, I'm talking about general covariance and so on, then I can choose any coordinates, and the coordinates aren't.
Well, I guess maybe the way to think of these x's as not being coordinates but vector fields that depend on these, and then when you do the nonlinear realization, the derivative of that vector field then can be interpreted as the object, so you get.
Yeah, I'm just, is there some kind of local frame that's involved? Because you just have, coordinates. That's my problem understanding, for example, even just, xi, pi, so xi here and now. It seems like a very special choice of frame, or choice of, or manifold. Very just special.
Yeah, I would agree with you, and I think the existence in the ODD case, the existence of this ODD metric on the 2D dimensional space means the space is flat. So there are indeed preferred coordinates. So it's not clear to me that double field theory can realize anything other than flat things which can be embedded in two-dimensional flats.
Well, in this case, the interpretation is that these indices that I have here are tangent space indices, but then when you do the nonlinear realization and get this field bind, then because the field bind index transforms under the rigid G, then these coordinates should be interpreted as with indices on the world volume rather than tangent space. This is exactly how it works in Borisov Orkiveski as well. So I guess maybe
There's something with a pair of antisymmetric indices, you tend to think of, it's a form. But a form has to be a form on some space, doesn't it? Can you have forms that are kind of not defined on anything? But then you have to have, but this is something else, because then they're not forms on space. The forms themselves are in some sense the coordinates, right? So you've got some antisymmetrized thing. So the question is, what do the indices mean? I don't get an idea of. That's the. So it somehow looks as though there's some linear transformation of whatever group it is acting on those indices. But that's very special, isn't it? You have some general manifold. You can choose any coordinates, and they don't transform in any particular way. It's only the other objects, vectors, etc., which on that space which transform in a particular way.
Yeah, so let's, you've got.
There's something about the whole setup that I don't understand.
You have an SL5 structure. So if we were just to write this thing out, let's stick with SL5. So we've got the 10. you know, I can't have a 10 by 10 metric that's an arbitrary 10 by 10 metric. I'd have far too much stuff. So I have this SL5 over SO5 structure. So it's very much reduced. I mean, you're reducing the space to allow that structure to happen.
So if you were doing Riemannian geometry in that 10 space, you could have O10, but you're saying no, actually the structure group is
I've got to
L5.
be careful. I mean, you have an SL5 structure,
Yeah.
which means that instead of having whatever 10 by 10, I would have an arbitrary metric in 10 dimensions. I have something where all the degrees of freedom come down to a metric in 4 and a 3 form in 4, which is much reduced. So it's not that you've got an arbitrary geometry in 10 dimensions.
Okay, but
It's
the
far
other
from it because
but you are saying you're saying a 3 form, and then my first thing, but the 3 form on what?
Three form on 4 dimensions because, and again,
Yeah.
perhaps this is the point, as he emphasized, up to solving the section condition. Right? So the section condition is going to mean that you're always going to restrict yourself to being, say, independent of y. And now you're going to say, well, why have I ever got y? Why? and so on. So, I mean, I think probably the point is, Paul, that for things to be well defined, you have to have the section condition. And of course, you have to have the fact that you've got this, well, in this case, SL5 structure. So there's two things that are related. And together, they allow you to extend the space. Well, Dan says no, it doesn't allow you to extend the space. Maybe it depends what you mean by extend
Well,
the space.
the space isn't really, because there's always this section condition, and sure that, you know, nothing makes sense unless the section condition is satisfied, and that exactly means that you don't have this extended space, but you're always coming down to, I mean, that this is sort of just a convenient way of describing it, but then you always have to solve this section condition and get down from 10 to...
The section condition looked like some sort of second order operator.
Yeah.
In fact, a rather simple one, right? So, I mean, one solution is, well, it's annihilated by the first order operator. That's the one you take.
Yeah, and that's the one that we was.
But it looks, can't one write down that it looks like, you know, it should be a linear something. Can't write
It
down
looks
the
like there
general
should be other
solution.
solutions.
You went in the whole first
No,
I thought you it was, no? No?
Everything would just be independent.
Ah.
Yeah, exactly. No,
So
half-
it's just the,
Or half,
the,
I see.
Yeah, if you look, it's an
extent-
anti-symmetrization.
I see, okay, yeah. Yes.
well, not half in this case, but
Well, yeah, of course. A subset.
But then there are other solutions that correspond to other duality frames, right? That's what
I guess I
and
don't
that seems
know.
like,
I mean, in ODD, that's what you do, right?
Yeah.
I mean, you know, let's come back to the ODD. We have X and X tilde, and one will be winding mode description. And one will be, you let the thing be independent of winding modes, you get usual supergravity. But I should also consider the other case, and if I have independent of winding modes, but kind of winding modes,
yeah,
then you get the T-dual.
Sure.
Right?
Yeah.
Nobody's arguing with that, surely.
No, I understand that, and
I'm looking at Dan. I'm trying to work out his
That's
argument.
fine when the space is flat, but I don't believe any of this extends beyond this, where this case where the space is flat.
Okay.
So these expressions make sense as expressions of sections of bundles over a d-dimensional space. To try and extend them into sections of bundles over a 2D-dimensional space, you can only do them in spaces when it's flat. So that's related to the question about introducing coordinates. When the space is flat, then there are preferred coordinates, and that's why you can think of these things as having the indices that they're trying. So for instance, think of some simple non-flat space like S3 and ask what the generalized, as we said at the lunch, ask what the generalized space is, what the 2D-dimensional or higher dimensional space is, and it's not at all clear what it is.
Well, in this case, we're never sort of taking this. We're never saying that the space is extended. As I just said, there is this thing that always. I mean, nothing makes sense, even geometrically, without this.
If you just never introduce the y's from the beginning as coordinates.
Yeah, I guess it's so whether the y's are there as coordinates to begin with, I guess, is a. I mean, it's used there to show in deriving the generalized metric, but I mean, as I've said in this section, they can't be treated. I mean, one can't think of this space.
Yeah, I mean, it comes down to whether, I mean, the section condition is there always, and that's always going to restrict you, and then. Any other questions? We've got another talk at 3, so I want to have a 10-minute pause though, so we can have tea or breathe, if the like. So let's just start a bit late. Let's start at 10 past 3.